What was they? What was they? Yeah, maybe. Not the. Yeah, it is. Right. So what was they doing with us? They was using us for batteries, right? You understand? Because we create what? So our sensors, what does our sensors do? It takes physical stimulus, converts it over to an electrical equivalent, so our brain can do what? Process it. That's what basically our brain is. Our brain operates off electricity, right? You understand? Our muscles operate off electricity, right? Y'all understand? So what does a sensor do over here? What do all these sensors do over here? Take physical stimulus and converts it over to electrical stimulus, so our processor can do what? Process it. So that's what a sensor does. It takes a physical stimulus and converts it over to what? An electrical equivalent, so our brain can process it, so those guys over there can process it. That's what a sensor does. So every sensor that we have on that manufacturing line, what does it do? It takes a physical stimulus, converts it over to an electrical stimulus, so our processor can do what? Process it. So that's what a sensor does. If you understand your senses, right, then you understand sensors that we use in motor control, or sensors that we use over there. So to have automated manufacturing, we got to have what? I know I recorded that on my. You're not telling what that sounded like. It was almost like pulling teeth, right? So when we all these sensors, and so over there we got photoelectric sensors. We looked at those. We got ultrasonic sensors. We look at those. We got position sensors. We got proximity sensors. There is a difference between a position sensor and a proximity sensor. A proximity sensor is a sensor that senses when an object is at a location. A position sensor knows where it's at within a range. Everybody understand that? So that's a big difference on those. What we have here, and that I've been working on, is we have a term called a servo motor. Anybody know what a servo motor is? Robert should know. He already asked. Yeah, it's a motor that provides feedback. So what are some of the things that we might want to know about a motor? Speed. What speed is running? What else? What might we want to know about a motor? Torque, yes. We might not want torque. We can get torque a lot just by the amount of current that the motor's running. If we know how much current that the motor pulls when it's running at its rated load, then if it pulls less current, then we know it's not developing the torque. If it pulls more, so we do that on our robots. We set torque limits. So that way, if something happens and the robot collides with something, it's not going to sit there and burn its motors up. It'll just kick it out, right? And say you exceeded the torque limit on the motor. But all they do on that, they got a current sensor that's doing what? Just sensing the amount of current that the motor pulls. And they have usually that's adjustable, so you can go into the settings of the robot and you can set the amount of torque limits that you set on your robot axis. Okay, so we said what? Speed. What else might? So think about the motors on those robots over there. Huh? No, we don't sense the size of the motor. What we're trying to do is sense what type of sensing that we need to have right on the motor. So Milton said a lot of times we need to know where the motor's at, right? The location. What position? We need to know the position of the motor. And another thing, we might want to sense vibration, but that's not one of the main things we sense. Vibration would be something extra. The motor usually don't provide vibration that's provided external. It's just like torque. Torque is usually not provided by the motor, it's provided external to the motor, right? You understand that? What we're talking about is what would a servo motor provide? What three things do we think a servo motor would provide? It's got of the three things, it's got to be a servo motor. It's got to give us at least one of those. But a robot motor gives us all three. It tells us the speed. It tells us the what? Position. And what else you think it needs to tell us? The direction the motors are running. Right? You understand that? Why don't you? So that robot can lower that thing down and it can raise it up. Well, to go one direction, it's got to run the motor clockwise. To go the other direction, it's got to run it counterclockwise. Okay. So we need to be able to verify direction because the direction depends on the position, right? You understand? So if I say 360 degrees, what in the world does that mean if I need to know what direction I'm going? So the three things a servo motor can provide is, we have a lot of them that provide speed. And that's all we need to do to control the speed. So if I got a conveyor belt that's only running in one direction, then I don't need to know direction, right? You understand? All I need to know is what speed is running. And that way we can control the speed. Okay. Robots have to provide all three of those things. It's got to know the what? The speed. So I can set the speed. I can say I want that thing to move at 100 millimeters per second. Well, how in the world does it know it's moving at 100 millimeters per second? It's got a sensor in there that tells it how fast it's going, right? Y'all understand? And then, of course, then we got to know, okay, I got to move over to here. Well, to move over to there and to position it, it's got to know the position, right? The speed, position. So if I don't know the speed, I can't set the speed. It's just like when you're driving in your car. So you have feedback. What do you do? So if you got cruise control in your car, what can you do? You can set it, right? You hit a set point. Well, it's got to know how fast you're going before it decides whether it wants to do what? Add more gas or take gas away, depending on what your car is trying to do. And of course, used to, in the old days, the odometer on your car didn't know direction. So, well, it did. And what would happen was people, when they wanted to sell their car, they'd jack their car up and they'd put it in reverse and let it run in reverse for a few days. And what would happen to the odometer? It'd go down, yeah. You know? So they took that feature away. So what we have here, that's real old cars. There was a show, there's a movie called Matilda. I don't know if you remember that. It's a cute little movie where the daddy used to disconnect it and put a drill up to the and run it backwards. So he didn't even run his car backwards because he used a bunch of gas. So one of the methods that's becoming really popular for motors is to use encoders. And we got two types of encoders. We have what we call an incremental encoder, and then we have what we call a quadrature encoder, or one of them's called a single channel, and the other one's called a dual channel. That's an absolute encoder. We're not going to look at those. You'll get those. So this is basically what an incremental encoder does. It just does what? Now, using an incremental encoder, we actually have a sensor, and then we combine it with another sensor that actually counts the blades. You know, see how that works? Pretty neat. So the rate, how fast, the frequency of these things coming by, that would give us an indication of what? Speed, but it doesn't tell us direction. That makes sense? So what they did is they came up with this method right here, where they have little sensors. Each one of them's offset by 90 degrees. So when one of them covers, one of them's open, the other's covered. What it does, it creates two channels, and they're 90 degrees out of phase, electrical degrees out of phase. So depending on the direction that it's turning, so here this channel is occurring first, so it knows we're turning clockwise, counterclockwise. If the other one occurs first, it knows it's turning what? Clockwise. So depending on which way these things are offset, it knows which direction. Not only does it know position, so these guys are equally spaced. So if it can count the number of blades, then it can do what? Position. If it can determine the rate, it knows what? Speed. And if it can figure out which one occurs first, then it can determine what? Direction. That makes sense? Okay. So this animation, it's only turning in one direction, but so this would be an example of a quadrant curve. Now here we're only turning counterclockwise, but if we turned it the other direction, then they would swap positions, right? Leading or lagging. Everybody understand that? So this is the little servo motors that we bought. These use quadrature encoders. So, it's a DC motor, but it uses quadrature encoders. It's a servo motor. So a servo motor is a motor that provides what? Feedback. The feedback that it uses is a quadrature encoder. So everything is built together. It's a gear motor, so this is the gearbox out here. Now what we're trying to do is we're trying to set the speed. We're trying to see the speed of this guy right here. We're not trying to see the speed of the motor, because this is the end of the motor that's doing work. Okay, do y'all understand that? So what happens, it goes through a gearbox. And it's 131.25 to 1. So what that means, this guy over here turns 131 and a quarter turn for this guy right here to turn 1. Everybody understand that? So what we end up with is this encoder here, it's got 16 blades on it. But what we're doing is we're looking at the position out here. So what we're doing is we get 2,100 pulses for every one revolution out here. So that would be the resolution of our encoder. That makes sense? So that means I can come up here, and if I can know that, then I can figure out how to do the position of the motor. Plus I can also figure out the speed of the motor, right? That makes sense. So, dang it. I'm going to try to put both of them up here. So here's my oscilloscope. I'll try to get a little closer. And so here's our encoder. This is, we call it channel A. And let me trigger on that, guys. So let me go to trigger menu. We're going to trigger on channel 1. Okay, so here's my trigger right there. So it should freeze now. Okay, everybody okay? Let me change the position so we'll see. So here's channel 1. Here's channel 2. Oops, I'm looking at the wrong thing, sorry. Oh, I don't know what's going on in channel 2. Oh, yes, I do. My scope is on times divided by 10. And you can see they're all set by what? 180 degrees. So this would indicate one direction, and I can't flip it on the oscilloscope, it always would be the same. So if I reverse the direction of the motor, then what would happen? They would shift position. I can't show that on the oscilloscope because the oscilloscope always references to one channel. So everybody follow me so far? So what we would do is, if I wanted to get the position, so what we do here is we get so for every revolution, we get 2,100 pulses per revolution. And that's on the output shaft, right? Not the input shaft. Everybody okay? That makes sense so far? Okay. So what we could do is if I could measure this frequency, then I can come up there and I could figure out the speed, right? Does that make sense? So what we had to do on the Allen Bradley is we set up a counter. Yeah, actually on the encoder only gives us 16, but that's on the encoder. Then we run that through a gearbox. Now what happens is when we run it through a gearbox can do one of two things, or a gear train can do one of two things. It can increase the speed, but if it increases the speed, it decreases the torque. Everybody understand that? And then if we decrease the speed, we increase the torque. So what they're doing here is they're dividing the speed by 131.25. Does that make sense? So that means my output shaft is only turning this divided by 131.25. So what we want to do is we want to find the number of revolutions on the output shaft. So what I'm going to do is I'm going to take that 16 and I'm going to multiply it by 131.25. And this comes up and gives us 2100. So that's what the encoder gives us 2100 pulses for revolutions on the output shaft, right? But it's got a lot higher torque. I can't stop this motor because the motor's running real fast, right? You understand? But my output shaft is running real slow because what I'm doing is I'm getting a torque multiplier. Everybody understand that? So we don't create energy. The only thing we can do is change its form. So basically we can say, okay, my output power is equal to torque times speed. Well, the problem is my input power and my output power is going to be equal, right? You understand that? And that's a lot of people don't understand that. So technically, if I'm here and we get our power from TVA, so we get our power from the Tennessee Valley Authority. If I turn on a 100-watt light bulb, how much power would they have to give? 100 watts. Because they're not selling current, they're not selling voltage, they're selling power. Right? You understand? But they're trying to get me that 100 watts from up around the Tennessee River, up on those dams there. How can they get me 100 watts from up there? Well, if they tried to put current through a conductor, every current has an R value, right? You understand? It's got ohms. If I put current through a cable, right? You understand? it's going to do what? A wire is going to do what? It's going to drop a voltage. So it would be impossible to give me 100 watts at 120 volts from the 10, because by the time they tried to get that 1 amp down here, right, you understand, it'd be what? It'd be gone. The wire would be dropping all my voltage. So what do? Well, the big formula, guys, is power is equal to V times I. So I would be equal to P over V. So if I try to send that at 1,000 volts, then my current does what? Drops down. So that's the way Alabama Power does, or that's the way all these power companies do, is they transmit it at an extremely high voltage. Which means because they're not trying to sell you current, they're not selling your voltage, they're selling your what? Power. If they can send that power at 750,000 volts, that means they could send 750,000 watts of power with 1 amp of current. That makes sense. But they can't bring 750,000 volts into my house because it's looking for ground, right? You understand? Everybody understand that? I think it's like, I can't remember, it is 11,000 volts to arc 1 inch in a vacuum or something like that. So that guy would be that guy, and that's why your high voltage lines have to be so high up off the ground, right? You understand? They have to be what? Really spread apart. So the closer they get to earth ground, they got to start doing what? They got to start lowering that voltage down, which causes the current to go up because they're transmitting power, right? Y'all understand that? And people get confused on that. They say, well, you know, when voltage goes down, current goes down. But we're not talking about the load. We're talking about the source, right? You understand? Now, when they get it to your house, it's going to be at a voltage. Right? And what's the 2 voltages that we use at our house? 240. What do we use 240 for? The high wattage devices. Right? And why do they do that? Yeah, Milton knows. It's not because it's more efficient, it's that we can use smaller gauge wire. Right? So higher voltage is cheaper to install and cheaper to control, right? You understand? Because we're controlling less current. But what's the problem with high voltages? What does low voltage have? What advantage does low voltage have over high voltage? Safer, right? So all your low wattage devices are running on 120 because it's safer, right? All your high wattage devices are running on 240 so they can use smaller gauge wire. No, high voltage is cheaper to install. Plus, it gives us the ability to install it in our house. Most of your electrical wiring in your house runs through your walls. It runs through a 2x4. The biggest hole you can make and still maintain the integrity of the 2x4, and this is if you put it in the exact center, is what? What is it? 3/4 inch. That's the maximum hole you can put, right? I think. You have to be in the center, too. You can't be off to one side. If you're off to one side, then you change the integrity of 2x4. So 90%, probably 99% of the wiring in your house runs through the 2x4. Right? You understand? And you're trying to run a 3, 4, 5 ton unit out there, right? Needs 2,400 watts of power, right? And you're trying to run that wire through your walls. You think about Alabama Power trying to send 750,000 watts at 240 volts. The wires would be bigger than I can stretch, right? You understand? So what it does when they step it up so high, it gives them the ability to use a smaller gauge wire, and also instead of using copper, they can use aluminum, which makes it cheaper. Yeah, so it makes getting the power down here a lot cheaper. Even though aluminum is right on the verge of being a semiconductor. Aluminum has 3 valence electrons. As soon as you hit 4, you're a semiconductor. As soon as you hit 5, you're an insulator. Everybody understand that? So aluminum is right on the verge of being a semiconductor. So it's got a pretty good resistance per 1,000 feet. So what I can do is I can come up here and I can say, if I wanted to get degrees, I can say 2,400. How many degrees in a circle? 360. And this would give me the number of pulses per degree. Everybody make sense? But most of these you can figure out. So if I get 2100 pulses for one revolution, then what would be for 180 degrees? It's going to be 1/2 of this, right? So I have my high-speed counter. What's neat about the portal? So what I would have to do if we was doing this in RS Logix 500 is I have to take a count and convert it over to a frequency, right? You understand? So what I would do is I would count for 1 second, and then that would give me my pulses per second, which would be my frequency, right? Does that make sense? Yes or no? So I've got a program on 1100. This might be the last one I had open. So now the problem we have with the counter instructions. So we have counter instructions that's available to us. So here's OB1. You can click on the icon and not the title ridge. For some reason I'm having a problem. So the problem we have with we're having with a regular counter is all these counter instructions over here. These are software counters. So they're implemented with software. The problem with software is software relative to hardware, software is slow. So the problem is I've got a 2100 count motor. We're running our output a maximum of 80 revolutions per minute. So if I've got 80 revolutions per minute, I'll come up here and multiply that by 1,000. I could take that and multiply that by so 80 RPMs on my output would give me times 131.25. This would give me the number of revolutions on the input. And this is RPM. So how many revolutions would I have per? So the motor's running a lot faster, right? You understand that? So how many would we have? So this is the maximum RPM on my output. So this is the maximum we should run this motor at, 80 RPM. Let's say, so I'd have 10,500 counts flying past that thing in 1 minute. And then I could come up here and divide that by 60. And how many would I have coming by in 1 second? What's that? 175 counts per second. There's no way in the world is PLC. That's no way in the world a software counter is going to keep up with that. So a software counter is implemented with programs, right? You understand? You can imagine the amount of code it would take to do counting. So the big advantage of hardware over software is hardware is a lot faster, but you're stuck with what you got, right? You understand? So what they've done on these PLCs is they put what we call them high-speed counters. These are hardware counters. So now our PLCs have these extremely high-speed counters in there, and they're hardware. They're not software. They're implemented with hardware, which means they can go at an extremely high speed, right? So the 1100 PLC that we had over on the in some of y'all the 1100s, I don't know if the 1000's got a high-speed counter or not. I can look. But the Siemens 1200 has 6 of these guys in there. So one of the things that we would need to do before we use the high-speed counter, so we don't address the high-speed counter. All we've got is an instruction that we can use to tell it what we're doing, right? Does that make sense? So this is a high-speed counter control block right here. So this is what we can go back and configure the high-speed counter to what we want to do. This, since it's hardware, where we would have to go to configure this? We're going to have to go to what? The PLC, go to what? Properties. And then this is where we would come in here and configure our high-speed counter. So this is where we configure our hardware, right? Everybody okay? So here's our high-speed counters. And the 1200's got how many on them? 6. Okay. So this is general information. We got it set to count up, which is not true. We're using what we call an AV counter. So this is the 2-channel counter. This is the quadrature counter. So what does that mean? Well, a quadrature encoder not only gives us position, it not only gives us speed, but it also gives us what? Direction. Y'all understand that? So this is what we call an AV counter. So these are the 3 we got. We can just make it a single-phase counter, a 2-phase counter, or an AV counter. This means it's a quadrature counter, which means it gives us direction. Then the initial values. So look how far the sucker can count. So close numbers, 1, 2, 3, 4, 1, 2, 3, 4. So you can go to 250, 147,483,647 positive direction, and one more negative direction. You call it 0, right? 0 eats up one of your positive combinations. So I left my counting a long time last night, and it still didn't go. We're not using sync inputs. We're not going to look at these, but we do need to specify which inputs that we're using. So you can use any input on the PLC. By default, it's using 0, 0.0, and 0.1, so I kept those. Are we okay? That makes sense? So I have my 2 encoders hooked up to these 2 inputs. I mean, my 2 channels hooked up. Then we're not using a hardware output. This is the I/O address that we're going to use for this thing. We can reassign this. This is a double word, so wherever we put it, it's going to be 4 bytes in memory, right? So by default, it gave it 1,000, which is way outside my range, so I got no problem. So it's 1,000 to 1,003. Everybody okay there? And then we have the hardware identifier. This basically gives us the ability to identify this guy to the processor. And this you cannot change. You got to remember. 259. Everybody okay? So when I come up and set up my high-speed counter, this is the control. So this is the high-speed counter identifier. And what did I put right there? 259, right? Does that make sense? I'm using input 4, so we got what we got clear. We got where we got current value. So this is the new value. So this I put 0, and then I'm using input 4 to. So every time I make input 4 active, it's going to load this value into the accumulator of the counter. So what am I going to do? It's going to reset the counter. That makes sense. Everybody okay? Makes sense. Continue. What else? And that's basically it that we're going to use. This is an error right here. So this guy right here is true anytime there is no error, and it's false when there is an error. This tells us when it's busy. So this would be like on the 500, this would be timer timing, right? You understand? And this would give us the status. This would tell us if there's any problem. Are we okay? Now, what I've got this counter set up for, this was really, really neat. I forgot to show y'all that. Oops, wrong thing, guys. This is another thing. Oh, my goodness. Oh, this is a count. This counter down here is doing speed. So when I look at this guy, and it's not quite working, I'm going to do this to do frequency. So on the Allen Bradley, your counters don't count frequency, but if you count it for 1 second, then it's counting frequency, right? Y'all understand that? Because frequency is cycles per second. But what they've done with this high-speed counter is one of the options we have available to us. Nope. No, I need to go back and look at that. We can make it count frequency, by the way. Is it this one? Oh, so this is, I'm sorry. So this is high-speed counter 1. This is high-speed counter 2. And we've got it set up to do what? Frequency. But it automatically counts for how many seconds? 1 second. So which is pretty neat. On the RS Logic 500, I had to set up a timer that would reset the counter every second. And I'm using single phase because this guy right here is getting speed. And this guy's not quite working yet, so we'll look at the other. So I don't know. We'll go ahead and see if it'll download. It might make, since I've had my PLC connected, it might have to go out and find it again. Oh, everybody go duh again. Duh. It's not going to find my PLC because I watch. I don't have it hooked to my computer. This setup's got a switch on it, so if you see that cable, and I don't know what a switch is, right? So what's a switch? Network switch. Gilbert, you should know that. Did you get that? Is that A+ network certification or hardware? Yeah, but I'm saying you should know what a switch is. So what type of topology do we use for a switch? Star topology, yeah. So when they first came out with the star topology, we use a device called a hub, and then all your computers, all your addressable nodes would come up here and connect to the hub. But all the hub was just a repeater. So what would happen is this guy right here is broadcasting data. It would go out here, and it would go out this lane, it would go out that 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 lane, even though this is the guy that I was supposed to communicate with. Well, what the problem is, none of these guys could put a packet on there, even if they didn't want to talk to this guy. So this guy was trying to talk to this guy, but now nobody else on the network could talk. Why? Because they would sense traffic on the network and they wouldn't talk. And these were hubs. Sometimes hubs were not even active. They just routed wire all over the place. Then we came to active hubs, which means you plugged them in, and then they were true repeaters. Well, what we wanted to do was come up with a method where we could reduce this traffic, so they came up with a switch. So the difference between a switch and a hub is that right off the bat, every time a computer is turned on, it starts broadcasting information that says, oh, I'm here. One of the things it broadcasts, it broadcasts its MAC address as part of the first packet. And what the switch does, it learns the MAC addresses for all these different computers. So what happens when I put out an IP address, it comes out with a packet, and then my destination MAC address is known. And so what your switch will do is it'll route your packet out to these guys, and nobody else gets the packet, because now it's switched, right? So it's actually switched between the source computer and the destination computer. So now this guy right here could communicate with that guy. This guy could communicate with that guy. This guy communicate with that guy. It can't communicate with this guy or that guy. It would get a collision and it would back off, right? If it's trying to. But what a switch did, it increased the speed of your network by magnitudes. So instead of one computer tying up a network at a time, it only ties up the link between what? It and the destination computer, right? MAC addresses, are those physical or logical? Access code. It's a 48-bit number. The first 24 bits identifies the manufacturer. I found I'll put the link on there, so you can look at the MAC address. And I found a site where you can just start typing in the first 4 digits, and it'll tell you the manufacturer of that network interface. It's pretty neat. So I have a switch right here, and we have 2 switches. They're 5-port switches. So later on, hopefully, when we get time, hopefully we can network these things together. So I didn't have it hooked up. So now it found it, so we're okay, right? And then we can go online. By the way, by default, when you deal with MD, so it's MD. MD. The double byte. MD would be what? Sorry, it's a double word. MD would be what? This is 16. This is 16. So MD would be 32. I got a write up on that too. So this is the way we identify. So ID, this is the double word, 1000. That's the address for my account. So this is the input of my account. Then I'm taking the output of my account. This is the output of my counter, my high-speed counter, and it's going to this guy right here. But what base by default? What base is it? Text. So what you do is you have to be online to do this, guys. Is you come down here under the tag, you right click on it, and then go to display format, and then you can come over here and you can specify a decimal. So that's the actual decimal. So I'm going to come over here on the same thing. Right click on the tag, go to what? Display format, and then we can go to decimal. And now we can see what's going on here. So right now we're going in the clockwise direction. So can you see what my counter's doing? Counting up. I'm gonna hit switch 4, so switch 4 should clear it out. Can you see what my counter's doing? Counting up. I'm gonna swap the directions on my encoder. And what's it doing now? Counting down, because it's a quadrature encoder. So what? I switch the power leads on my motor and make it turn in the opposite direction. It won't go, it don't like that. And you can see, well, we'll come up here and increase the speed. So we're doing about 80 revolutions per minute. So not only does it know this, but it also knows direction. So I haven't written the program here yet so we can actually do position. So now it should be counting up, right? See that? Y'all want to set in here until it gets up to 2 billion? We could probably leave it running at this speed for a week and it probably still wouldn't get there. But let's slow it all the way back down. Okay, so now we're going in the positive direction. And I'm going to stop it. And what I'm going to do is I'm just going to move the flat surface. Okay, so it's pointing at the camera, right? And then I'm going to reset this thing. So that's switch 4. Okay, so I want to make it go 1 revolution, come back to this exact same spot. What count would I be looking for? What we're going to do is we're going to spin it in the clockwise direction, and I want to stop it right here at the same spot that it stopped at now, pointing right at the camera.
And you don't know how much increase?
Yeah, what count should we look for? Huh? Can't be an or. Huh? No, I'm trying to say how many counts would it take to bring it back to this same position without even looking at it. What I'm going to do is I'm going to look at my count. I'm not going to look at the motor. I'm going to look at my count. It's 2100 per revolution. So I wanted to count 2100, right? You understand? So hopefully I can come up here. Huh? Yeah, I'm sorry. So here we go. I'm looking at my counter. This is going to be touchy because you got to get off of it because the motor coast. So it should be pretty close to pointing right back at me, right? Okay. So what I have to do is I can come up here and I could calculate a count per degree, right? You understand that? So I could take 2100 and I could divide that by 360 and that would give me the count per degree. You understand what I'm saying? Yes or no? Count per degree. It's telling you the way you would actually do the math. So it says counts per degree. So what I would do to come up in my program, if I wanted to run it to an exact angle, then I would take the total number of counts. What's our total number of counts per revolution? 2100, and I would divide that by 360. That would give me my counts per degree. And now if I wanted to run it 90 degrees, y'all understand? Yes or no? Okay. So what would our counts per degree be at? 5.83, yeah, it's going to be odd. So what I would do, and this is degree, this is, right, y'all understand that? This is, so I could come up here and say, okay, I want to make it turn 180 degrees. Well, then I would take 5.83, and then I would multiply it times 180 80 degrees, and then that should give me the count. We should be half of 2100. We know that. We can check it, right? Huh? Yeah. Which is half of 2100. So what I can do now, once I've got this, we call it a transfer function. Once I've got it that, now I can relate what? And what I could do is I could take this and just put it in a multiply instruction. So I could take my count, right, you understand, and then I can multiply it by that, and then let it do the math for me, right? Make sense? And then compare it when it got up to that a certain value. So the speed of the pulses would tell me the what? The speed. Which one leads and which one lags would tell me the direction, and then the number of counts would tell me the actual position. So these are quadrature encoders. This is a servo motor. It means it provides feedback. There's three things a motor could give me. It could give me speed, it could give me position, or it could give me direction, right? And this gives us what? This gives us all three. That's why it's got so many wires coming out of the back. Because not only do you have to control the motor, you have to power up the encoder. So the encoder's got its own ground and got its own power. And then you got the two channels coming out of it. Direction. So notice, so we're doing all that right here. Then we played around with position. Of course, that was kind of fundamental. It was just me looking at counts. But we have, the problem we have with these encoders, these incremental encoders, is that you have to give it a reference point. Because this count means nothing if I just come over here and do what? So I have to start counting from 0. So what I did is I positioned the encoder on where I wanted to stop at, and I moved it around. So I positioned the encoder on where I wanted to stop at, and then what I did? Then what did I do? I came over here and zeroed it out. Now I have a reference point, right? That now the position means something. So an absolute encoder gives you a position. An incremental encoder, what it does is you have to start it from a reference point. So all the robots over there, we have what we call an origin point that we have to establish. And that's where it counts from, right? Does that make sense? So that's why all the robots have batteries on them. Because if you lose the origin, then we're what? We're lost, right? Does that make sense? That would be like I come over here and spin this a little bit, and then I come over here, right? Or I came over here and moved it right there. What did I just do? I've lost my reference point, and now it makes no sense where we're at. I get a count. Sure, I get a count, right? But it don't make any sense unless I can do what? Unless I can come over here and put it at a certain position. This is as slow as this motor will run, right? And then what can I do now? Then I come up and I zero it out, right? And you can see what that's doing now. So what it does, and you can set this to any value that you want, guys. So what you do is when you hit that, so here's my switch. Y'all can see me flipping it now, right? So when I flip that switch, what it does, it loads whatever I decide to put right there. So what am I doing? I'm loading it with 0 every time. But you could come up and you could load it with any direction you want to. Are we okay? You can make it physically change direction. So if you make this true, then this input right here would determine whether it counts up or counts down. We have it set up for a quadrature encoder. So the quadrature encoder tells it which direction it's going. And the counter automatically counts up if it turns, counts down if it turns counterclockwise, and counts up if it turns. Yes, we can. Then we'll come back and go lab. Everybody okay?